How to find the Bode plot, frequency response, and transfer function of an analog filter in the form of a bandpass filter that is shown in this example and walkthrough video. I would like to show a quick way to find these and also show results from Matlab. So at the input of this multi-stage filter, we have Vn coming in, which when we are doing sinusoidal steady-state analysis, it would be a sinusoidal signal with a frequency omega. We will get to that. The first stage is just made with one op-amp and one RC. And the second stage is made again with another op-amp and two capacitor and two main resistors. So let's make the assumption that op-amps are properly biased. The supply voltage, let's say plus minus 5 volt, are applied. You can see that output of op-amp via this wire, for example, properly connected to inverting or negative input terminal, indicating negative feedback. That's good. So negative feedback will enforce a properly biased op-amp to linear region of operation. And then the same thing for op-amp number 2. You can see that we have applied properly the supply voltages, and then via this connection we have proper negative feedback from output to inverting input terminal. So that's good. Now that we have op-amps properly biased with negative feedback, we can say that negative feedback enforces virtual short, which means that the voltage at the positive input terminal is equal to the voltage at negative input terminal for op-amp. So, for example, in op-amp 2, positive terminal effectively is grounded via RP. RP is only for matching purposes, that resistor RP. So, voltage at positive terminal or non-inverting terminal for op-amp 2 is 0. Because of virtual short enforced by negative feedback, voltage at negative terminal should be 0 or effectively a virtual ground. The same thing for op-amp 1. Whatever we find as the voltage at positive terminal will appear and will be at the negative terminal as well, enforced by the negative feedback. So with that in mind, let's focus on the first stage. It's a low-pass, first-order low-pass filter effectively. The reason for that is at super low frequencies, or let's say at DC, this cap C1, capacitor C1 is open because the impedance of cap is 1 over CS, or effectively, if you're doing sinusoidal steady-state analysis, 1 over JC omega. At frequency DC, omega is 0, so impedance goes to infinity. But effectively, it means cap is open. If cap is open, there is no current flowing because nothing can go through the op-amp, and therefore Vin appears at exactly positive input terminal of op-amp. Because of virtual short, Vin will be here as well, and Vin will be at the output of this buffer stage. All I'm trying to say is at super low frequency, Vin appears at the output of this as expected, as it is supposed to be a low-pass filter. At super high frequency, the impedance of cap effectively, when omega is much large in denominator, the whole impedance goes to 0. So effectively at super high frequency or high enough frequency, this cap is shorted to ground, and therefore it will enforce that the positive terminal is grounded, which then, because of virtual short, will enforce a virtual ground at negative terminal, enforces 0 at the output as expected. So intuitively at super high frequency, output is 0, nothing passed through this stage. At very low frequency or DC, Vin exactly appears at the output as expected. So it's a low-pass filter. So that's the intuitive approach to understand and analyze this. But then what I can say is this one. Now that I know this is a low-pass filter stage, so here is a first order low-pass filter, I'm going to say the Vin to Vx, if I refer to this node here as Vx, the voltage at this intermediate node, then I'm gonna just write the transfer function from Vin to Vx. So Vx is equal to, so Vx will be here. Because of virtual short enforced by the negative feedback, Vx is exactly here as well. And we can see that from Vn to Vx is just a simple voltage division between cap C1, capacitor C1, and resistor R1. So we just do that. It's 1 over, and let's stick with the S-domain circuit analysis and impedances. So 1 over C1S is the impedance of this cap, and we are doing a voltage division. And then R1 in series with C1, because no current can flow through the positive terminal of or negative terminal of ideal op-amp, because input impedance is effectively infinite. So we have R1 plus 1 over Cs, and then this is Vx as a function of Vn. Or I can write it transfer function of the first stage, which is effectively Vx over output of this first stage divided by input in S domain, is equal to, just clean this up, we get 1 over 1 plus R1 C1 S. Great. Okay, so one just quick calculation here, of course. R1 C1 is just 10k times 500 picofarad. So if you compute that, you will see that R1 C1, sometimes people refer to it as tau 1 because it's time constant, is just again 10k times 500 picofarad. In this example, that turns out to be just 1 over 200,000 in second. That's for R1 C1. Alright, so let's keep that in mind for now. That's for first transfer function, H1s transfer function of the first stage. Now, let's focus on the second stage now. In the second stage, starting from Vx and going to the output. So we have a second order filter, which intuitively I can show you it's a bandpass filter. Let's take a look. At DC, for the same reason I mentioned earlier, this C2 with impedance 1 over C2s or 1 over C2 j omega, when omega is 0, denominator is 0, impedance goes to infinity. This capacitor C2 is open at a super low frequency close to DC and DC, and that would not allow signal passing, DC signal passing through it. It's effectively a decoupling cap. So with that, if we are DC, nothing goes through, output remains 0. Now, so we know that this second stage doesn't pass DC. What about super high frequencies? At super high frequencies, what happens is this is shorted because impedance of cap is 0 at super high frequency or high enough frequency. This cap is also shorted. When this cap is shorted, it is shorting or connecting output exactly to input. But the problem is, if that happens, because of the virtual short, the positive input and negative input terminal are shorted, enforced by negative feedback. Positive terminal is at 0, so negative terminal is at 0. Therefore, the moment Vout is shorted to negative terminal, Vout becomes 0. So that means for super high frequency or high enough frequency, output also is 0. So we found that for the second stage, this stage, DC doesn't pass, super high frequency doesn't pass. It's a clear indication that if x-axis or omega is the frequency or radiant frequency, and if this is output, we don't have anything at low enough frequency and we don't have anything at high enough frequency. So whatever happens is mid-band frequency that filter would allow things to pass through. So it's a clear signature of a bandpass filter. Okay, so this second stage is a second order bandpass filter, BPF. I intuitively show why it's a bandpass. Why second order? Second order mainly just because you have two set of RC, C2 and C3. So that's an indication that we have two poles involved. It's a second order filter. Alright, so since we have a first order low pass filter at the beginning, and then we have a second order bandpass filter as the second stage, the overall impact is a third order bandpass filter. So we are dealing with so overall cascade of these two, which let me show it this way. So we have V in coming in, and then we have the first order low pass filter, and then we have the second order bandpass filter, and then we have output. So effectively the overall system is a third order with 3 poles. You can see here we have a pole. So with 3 poles, third order bandpass filter that I'm going to analyze and find the Bode plot, frequency response, and transfer function. But intuitively we examined it. That's one important step to make sure we understand how the circuit is working. Okay, so let's focus on the transfer function of the second stage, which is a second order bandpass filter. So from Vx, from Vx I am going to Vout. You can see what we have realized using this second op-amp effectively with the topology of this second op-amp, in the sense that output is connected to inverting or negative terminal. It's an inverting amplifier. So second op-amp is in the form of an inverting amplifier. And what I can say is effectively it can be written quickly, but one very systematic way of looking at it is we know that the negative terminal here is 0, and we can write a KCL or Kirchhoff current law that says the current that is flowing this way cannot go through, in this case should be equal to the current going out. So there is no current going this way because input impedance of ideal op-amp is practically infinite. So this whole current has to continue flowing through C2 and R2. I can write KCL relating or setting equal this current equal to this current. So these two currents should be equal to each other. That's all I'm doing. So let's do that. So for KCL written at a negative terminal of op-amp 2, I can write, what is this current? Easy to compute. Vout minus 0, that's the voltage drop across C3 and R3. So I can just divide that voltage drop by the overall cap to find the current. So I can say that current, or let's say the current that is that current, so this current I, is equal to Vout minus 0, or effectively just Vout, and then time admittance, or 1 over impedance. Admittance, these two guys are in parallel. Two impedances in parallel, they have the overall admittance is the sum of admittances. So it's 1 over C3s, that's the admittance of cap, plus 1 over R3. So that's the current. Now, equal to this current. So what is this current? It is again the same thing. We have the voltage drop across R2 and C2 is Vx and 0. So 0 minus Vx given the direction of the current, which is this way. So I have 0 minus Vx divided by the impedance. Impedance, these two guys are in series. The resistor R2 and capacitor C2 are in series. So I can say just R2 plus 1 over C2s, again S-domain analysis. Okay, so in summary, what do I get out of this? What I get out of this one is this. I am going to write it here. So here, I get Vout, if I clean up, over Vx is equal to minus R3 C2s divided by 1 plus R2 C2s 1 plus R3 C3s. So that's you can refer to this as the transfer function of the second stage. So Vout as a function of S, Vx intermediate node as a function of S. I can refer to this as H2 of S. Okay, so that is my second transfer function, and obviously the overall transfer function, because these two stages are in cascade, would be just, and we are dealing with linear systems, the overall transfer function is H1s times H2s. So I can say that therefore the overall transfer function of this bandpass filter is this guy. So 1 plus R1 C1s, that is H1 of S, and then all the components including the negative sign from the second stage, which means minus R3 C2s 1 plus R2 C2s 1 plus R3 C3s. Okay, we found the overall transfer function of the whole bandpass filter here, and as we analyzed before, there is one 0, basically S equal to 0, when we set the numerator to 0. And there are 3 poles by setting each of these components to terms in denominator to 0. So if we set to 0, we get pole number 1 equal to minus 1 over R1 C1. If we set this equal to 0, we get pole number 2 equal to minus 1 over R2 C2. And if we set this equal to 0, we get pole number 3 equal to minus R3 C3. Given the R1 C1 values and R2 C2 and R3 C3 values, if you compute these guys, you end up with, as we did for, say, R1 C1 here. So we did it here in second. There you go. This is R1 C1. So we found that R1 C1 is, as a reference, just minus, if you invert the 1 over 200,000 in second that we found for R1 C1, this becomes 200,000 or kiloradian per second if we translate this to j omega. So let's keep that in mind for now. And then for SP2, if we find SP2, it becomes negative 20 radian per second given the values of R2 C2, which are 100 kilo ohm and 500 nanofarad for these two cap and resistor and capacitor. And if we do this for SP3, coming from these guys, R3 and C3 cap and resistors, we find that this one is minus 220 kiloradian per second. Okay, so what is this? What is this saying? If we just want to plot, let's say, the pole zeros of this system, it would be as simple as this. I'm going to show it here. So let's say if we show the poles and zeros of VSD 0 is at S equal to 0, this is S plane. So I am showing S plane. And here we have a 0 here corresponding to S equal to 0. Then we have a pole at corresponding to SP2 at 20, let's say this one, 20 radian per second, SP2, so very small. This one is on the negative side, of course, and here is the real part of S. So this is S domain or S plane, and we are dealing with real part of S. S is general complex number, and then imaginary part of S. So we have 20 radian per second, that's SP2, and then after that the next one is SP3 in terms of negative 20 kiloradian per second, so it's like here, far away, minus 20,000, 20 kilo. And then here, far, far away then, we have the SP1, which is negative 200 kiloradian per second. So negative 200,000 radian per second. So this is the pole zero scheme of this. And what happens is, if from H of S, by substituting S equal to j omega, we want to get to the frequency response, what we get is, so I'm going to substitute S with j omega. So substitute S with j omega, and as a result what we get, H of j omega, or just H of omega, is minus j, so substitute S with j omega wherever you find it, minus j R3 S3 omega, and then denominator 1 plus one thing we can do, we can factor out R1 C1, R2 C2, and R3 C3 from denominator. If we factor them out, then they are going to stand outside. So R1 C1, R2 C2, and R3, let me correct this, this is C2, R3 C3, and then we have 1 over R1 C1 plus S, which is j omega, but then 1 over R1 C1 is what we found as, let's see, in this case would be the example that we found. It's just purely j omega 1. So it's, I'm going to just keep it as it is, but then we know the value. It is just the value that we have. So it's negative 200,000. So I can just replace that later. So it would be 1 over R2 C2 plus j omega, and it would be 1 over R3 C3 for the final term in denominator, j omega. I substituted S with j omega wherever I find them. And by the way, the value of, given the value of R3, which is 200 kilo ohm, and given the value of C2, which is 0.5 microfarad, we can see that the value of R3C2 in this circuit is just 0.1 if we compute that. So in summary, I just want to replace the numbers for the reference so that we can just go ahead with this is frequency response, the formula. So the transfer function replaced by S equal to j omega. So frequency response is h of omega equal to minus 0.1, which is substitution for R3C2, and then we have j omega, and I can also substitute effectively 1 over R1C1, 1 over R1C2, and 1 over R3C3 with the values that we computed earlier. So it will be 20 times 20,000 times 200,000 times j omega. That's the numerator. Denominator as simple as j omega plus, we can just write it in a just nice order. So 20,000, and then j omega. J is just the complex. So for the reference, j is what is the symbol or notation for a square root of -1. So j omega plus 200,000 that we have. So this is the frequency response for this example. Reason I wanted to highlight this, especially now that we know where the poles and zeros are, is because now I can show the Bode plot for this example. So just again, before Bode plot, take a look at what's happening. What is the h of 0? When h of 0, you can see that denominator remains some value, because when you substitute omega with 0, denominator has a value. But then numerator, when you set omega to 0, h of 0 is 0. So as expected, and of course this translates to if you're supposed to take a 20 log 10. So let me just write it right. 20 log 10 absolute value of h of 0, which is the way that usually we show the Bode plot or frequency response plotting, then 20 log 10 of 0 of course goes to -infinity as expected. So that's one thing to notice, and effectively you can see that as omega approaches to 0, then denominator effectively we can neglect j omega because it's super small as omega approaches to 0 versus compared with 20 and 20,000 and 200,000. So effectively denominator when omega approaches 0 becomes just a simple number. Multiplication 20 multiplied by 20,000 by 200,000, but numerator is effectively a number multiplied by j omega and a negative sign there. So all I'm trying to say is when omega approaches 0, h of omega or transfer function of overall system approaches just a number k, which is 0.1 times 20 times 20,000 times 200,000, and then times j omega. So and then minus is just effectively e to the j pi. J is e to the j pi over 2 or 90 degree, and k is a constant, omega is omega. So in summary, we get k omega times e to the j 3 pi over 2 or 270 degree. So you can write this as also e to the j 270 degree, or alternatively k times omega e to the minus j 90 degree. That's the same thing as 270 degree. So we expect that at omega 0, the response of the system or filter is 0, and the phase response is minus 90 degree. So that's what I wanted to start with for the Bode plot. And for when, on the other hand, when omega approaches infinity, given the transfer function we found, then when omega approaches infinity, j omega in all the terms in denominator is going to be much larger than whatever number we have in front of j omega. So denominator becomes j omega to the power 3. effectively when omega approaches infinity or becomes very large, and numerator remains minus k times j omega. So minus, instead of minus, let's keep it as minus, that's fine. So minus k times j omega. If we simplify this, minus k j omega, and then we have j to the power 3, which j to the power 3 is minus j, and then omega to the power 3. So minus j cancel out with minus j, and it becomes k over omega squared. So all I'm saying is, when omega is large enough, or we are dealing with super high frequencies, then the transfer function of this system approaches a real number. So that is an indication that phase will be 0, which I can write it this way: e to the j0, because e to the j0 is 1. So phase at infinity goes to 0 degrees, and at infinity the transfer function is a real function, and you can see we are dealing with denominator omega square, which means at infinity, if we take a 20 log out of, so I'm going to write it here. Again, these are prelude to the Bode plot, so that we don't need to make a lot of assumption for the Bode plot, and it's intuitively understandable why Bode plot will look the way that I'm going to show, and then confirm with Matlab. So omega goes to infinity, then what we have is 20 log 10 of, as we showed, in this scenario the transfer function converges to this, which means 20 log 10 k omega over omega square, which means 20 log 10 k minus 20 log, minus is become because we are saying 1 over omega square, and then I'm going to push the exponent to the outside, writing minus 40. So minus 40 log base 10 omega. This is 40 dB per decade. What is you will see in the Bode plot. So as the frequency, whenever the frequency increase in this regime, at regime of super high frequencies, whenever the frequency increases by 10x or 10 times, as a result of that, the frequency response drops or reduces by negative 40 dB. So that's the meaning of 40 dB per decade drop. So let's keep that in mind here for the Bode plot. So now the Bode plot plotting, I'm gonna show it here. So we have x-axis the frequency in radian per second. We have at minimum 0 DC. So at DC, and this is what we refer to as 20 log 10 absolute value or magnitude of omega, h of omega, or the frequency response. So this is magnitude response Bode plot. So what do we have? At frequency 0 or DC, as we talked about, and remember this is the 20 log sketch. So in 20 log term, when frequency is 0, we know the linear value of h of 0 is 0. But then 20 log of 0 is negative infinity. So I cannot show negative infinity. What I can show is effectively we are coming from negative infinity, but as frequency is increasing from 0 DC toward higher frequency, the transfer function is now increasing with a slope of 20 dB or decibel per decade. Decade meaning that every 10x increase in frequency, and the reason for that is this omega appearing, because as I said, when you take a 20 log 10 absolute value of h omega out of this guy, we don't care about the phase because absolute value removes the phase. We care about k omega, which means it becomes 20 log 10 k plus 20 log 10 omega, this component here. So that 20 log 10 omega is reflecting the fact that every time omega is increased by 10 times in this regime, then we have a 20 dB increase. So let me write it here. 20 log 10 10 omega is equal to 20 log 10 10 plus 20 log 10 omega. This is 20. So it's 20 plus 20 log omega base 10. So that's it. Every time you increase omega by 10 times, then there is a 20 dB plus the frequency response showing up. That's why we are saying 20 dB per decade. Every 10x, another 20 dB, this thing is going up. So, but where is the point this stops? It's exactly at 20 radian per second. Why? Because at 20 radian per second, the first pole shows up. So at 20 radian per second, the first pole shows up, counteracting the effect of the zero. So take a look. When we are at, let's say, just as an example, when we are at 2000, let's say when we are at 1000 radian per second, so here let's say is 20 radian per second, but when we get to 1000, and I'm not properly showing it on the x-axis, but let's say when we get to 1000, it's sizably large enough compared to 20 that we can neglect 20 compared to 1000. So when you substitute omega with 1000 in the denominator, effectively we can neglect 20 and we can write this term as just j omega for the range of omega equal to 1000. But at the same time, j 1000 is negligible compared to 20,000 and compared to 200,000. So for these two, we can neglect j omega in terms of absolute value. We can just consider 20,000 and 200,000 that cancel out with the 20,000 and 200,000 in numerator as well. So what remains when you are at this range of omega 1000? What remains in transfer function is, or frequency response transfer function is in the form of let's say my absolute value wise, so I don't care about the negative sign in absolute value. So 0.1 times 20, these two canceled out with denominator as I talked about, so it become times omega. I don't care about j because we are talking about absolute value, and then divide by, as I said, these two goes away because they are 20,000 and 200,000 that cancel out with the 20,000, 200,000 in numerator. This one is just j omega. So I don't care about j, because we are dealing with absolute value. Omega remains c. These two cancel out. Transfer function in this range, when we are sizably larger than 20 and less than 20,000, which is the next pole. When we are in this mid-band range, the transfer function simply becomes 0.1 times 20, which is 2. Nice. So we expect that the transfer function linearly in the mid-band or band in the pass band to be just 2 linear, but this is log scale. So I need to show 20 log based, so I'm going to write it here, 20 log base 10 2, which is 6 dB. So I'm going to write 6 dB here. In the pass band of this bandpass filter, we have a constant 6 dB in dB scale in the magnitude Bode plot. Okay, so this is the way that the frequency response of this bandpass, third order bandpass filter looks like. This is how it's looking like, and then we have this up to the second pole. So that is the first pole. This is the second pole. And that's the end of the passband. When we hit that second pole, what happens is we start now dropping because the impact of the second pole kicks in and tries to reduce the magnitude of the output by 20 dB per decade. Same slope as this one the other way. So it will be now 20 dB per decade drop. So maybe I show it better this way. This is 20 dB per decade, 20 dB per decade drop. And then after we hit the final pole, which is the third pole at 200,000, so at 200K, we're gonna have the impact of the second pole kick in, adding another 20 dB here. So that's why I'm showing the faster drop slope, which is now effectively total of 40. So here, if I show it, this will be 40 dB per decade. Every 10 times from this point on, from 200,000 radian per second onward, every 10 times increase in frequency resulting in 40 dB further drop in the magnitude response. So it becomes therefore 40 dB per decade. This is the Bode plot magnitude response, and what I would like to show that in real life it's not exactly this. This is asymptotic, but very good high-level understanding of the behavior of the magnitude response of this filter. In reality, the magnitude response looks like this. So looks like this, and the gap here between the actual Bode plot, between the actual response and Bode plot, is about 3 dB, and about 3 dB here as well. That's because in reality we have imaginary component in denominator. So if you want to see what Matlab is giving us with respect to this, is here is a plot in S domain frequency response that I'm showing, that is plotted using Matlab for both phase and magnitude. So there you go. You can compare that with what we found here, exactly matching. See, this is the magnitude. Let me just show it in a better fashion. So here is the magnitude response, and we have at, let's say, 0.01 radian, almost close to DC, we have, and this is shown in the sort of a linear fashion, but in a logarithmic plotting. So we have, we are starting to go up with 20 dB per decade as shown in Matlab plot. And then when we get close to, say, what we expected, about, so this point is 10, so this next is 20, that's 20 radian per second, and then there you go. At this point, we are 3 dB below, and this peak, which is now the range that we have a passband, is exactly hitting at 2. Which means 2 linear, which means, as I said, 20 log 2 base 10 is 6 dB. So this is at 6 dB or linear 2. And then when we get to close to, say, 20,000 here, this is 10,000, this is 20,000. We have exactly the point that we get 3 dB below the flat line, which is as we expected. And after that, you can see initially we have slower slope, but then it sort of ramp up after around 200,000. Here is 100,000, and here is 200,000. At around 200,000, now from 20 dB per decade, we get to 40 dB per decade drop. So this is exactly matching what we found without even plotting. So you can see the impact of 20 dB versus the impact of 40 dB. This slope is obviously considerably larger than this, effectively twice. This is 40 dB per decade. See, let me just highlight it as an example. So from here, so let's say from here, which is 1 million radian per second, to the next line, which is, so from 1 million to 10 million, so that's exactly 1 decade of frequency increase. You can see that the magnitude is dropping by 2 orders. That's exactly in dB scale 40 dB. So we have that in mind. But in the case of 20 dB per decade, you can see that when we have 10x increase in frequency from, say, 0.1 to 1 radian, we only have 1 decade increase. So 10 to the minus 2 goes to 10 to the minus 1. So that is just a visualization of that expectation. So what is covered up to this point? We have covered the intuitive understanding how this filter is working. we have found the S-domain transfer function. We converted that to j omega, or omega transfer function, or magnitude response and phase response. We analyzed what sort of a phase and magnitude we expect at DC and high frequency. From there, we also found the pole zeros, and then we also plotted the pole zero map. And then from there, we got to Bode plot, which is also confirmed with the Matlab Bode frequency or magnitude plot. So also as a side note, we examined that at close to DC, the expectation for the phase is minus 90 degree, or effectively 270 degree. And at super high frequency or large enough frequency, as omega goes to infinity, the expectation for phase is 0 degree. That's exactly what is also confirmed by Matlab phase Bode plot. See, at super low frequency, like 0.01 radian per second, close to DC, we are at phase degree almost negative 90 degree, matching our expectation. But then, as we are increasing the frequency, phase is further dropping. When it gets to minus 80, 180, so minus 180 degree, Matlab, what it does, automatically do a wraparound and jump to plus 180 to sort of keep the phase always between minus 180 to plus 180. And then after that, as more poles are introduced, so this reduction is the impact of the first pole. But then when we are hitting the second pole of the system, then we can see that further reduction is happening. And finally, with the second and third pole, with the second and the third pole, what we are seeing is we observe that from the 180 degree, we get to 0 at very large frequencies, like 10 million or 1 million roughly. So as expected. Remember that for phase Bode plot, or phase, the impact of each, let's say, remember that the impact of each pole is just 90 degree reduction. So we have 3 pole, and initially we started with, at the DC, we started with minus 90 degree here, which is effectively 270 degree. Because e to the j 3 pi over 2, which is 270, is the same as e to the minus j pi over 2, which is minus 90. Starting from 270, since we have at DC, since from DC to large enough frequency, we are introducing 3 poles in this system at 20 radian per second, as 20,000 radian per second, and at 200,000 radian per second. Therefore, each pole is causing negative 90 degree, or effectively negative 90 degree. Adding them together, negative 270 degree. So no wonder from the initial 270, by this reduction at super high frequency, we get to 0 degree. So that's the analysis of what's happening with respect to the phase of this filter. Okay, I hope that this extensive Bode plot, frequency response transfer function, pole zero, and intuitive analysis of the behavior or response of this bandpass analog filter is helpful and useful. Thanks for watching.